Hello everyone and welcome back to PC Retro Tech. Regular viewers will know there haven't been videos for a while and I'm here to explain what happened. Recently I purchased an Amstrad XT class machine, in fact the final machine in their XT line, and I got it very cheap and unfortunately it had a few issues. I went to repair it and it blew up, smoke and all. So I've actually been spending the last few weeks to months, I think, repairing that machine. It's been very slow. It's proprietary. You can't just go out and buy replacement parts. But I am making progress, and I do expect a video on it eventually on the channel. Now, my interest in that is the graphics subsystem. Amstrad improved that throughout their XT line of computers. And while we're waiting for that video to come out, I thought it might be interesting to go back to the very first XT they produced, the PC1512, and do a much deeper dive on the graphics subsystem in it for comparison. Now, the reason this is interesting now is because recently I worked on some techniques for doing cycle accurate probing at the register level. One of the chips that was in the original IBM color graphics adapter that was found in the IBM PC and in XTs like the one behind me here. And we discovered all sorts of glitches and were able to figure out on a cycle by cycle basis how that chip worked. This machine is based on a similar technology. It is a CGA machine with an additional 16 color graphics mode and some additional graphics RAM. It's a little bit slower in the way that it operates. It uses a custom chip that Amstrad developed, and to my knowledge, the same sort of cycle accurate reverse engineering has not been done on this machine. And the sky's the limit here. We could literally discover a new graphics mode or some new glitches that can be exploited, or at the very least figure out what the wait state schedule is so that we can work out an optimal way of putting data into video RAM. Now, there's a reason to do this. This machine was very popular in Europe. It sold well in the UK, Spain, France, Germany under the name Schneider, and actually also in Australia where I'm from. In fact, the very first PC of any kind that our family owned was a PC1512, so it's very dear to my heart. So I'm really looking forward to what we uncover here. It's very exciting, and you saw it here first on PC Retro Tech. So let's get stuck in and see what we can find. It might seem a little bit odd to have the cover off this when I said I would reverse engineer it with software, but there's a few things I need to know about this before I can get started. First of all, I need to check that the CPU hasn't been upgraded to an NEC V30 and that the original 8086-2 CPU is in there, and it is, so nothing to worry about there. The other thing I need to know about is the memory. These are 41256 chips, and there are 18 of them. So basically each of these is 256 kilobits by 1 bit. And so that means that if you have 8 of them, then you have 256 kilobytes. So 2 lots of 8 would be 512 kilobytes, hence the name of the machine, PC1512. And there's a couple of other chips for parity. Obviously you can add some additional chips here to bring the total up to 640K, but those chips are not here. Now, the important thing about these is that these are dynamic RAM chips, which means that they need a pulse every few milliseconds to refresh the contents. Otherwise, the machine will just crash. Now, we're going to try and turn that pulse off, if it's even possible with this machine, and do the dynamic RAM refresh ourselves so that we can get cycle accurate timing of the machine. And that's why I need to know how often that pulse occurs. It turns out that these require refresh every 4 milliseconds. Now that's a little bit more often than 4 times per graphics frame. The monitor of course runs at 60 Hertz. So that's the critical information that I need about these chips. Well, I may as well go through some of the other chips while I've got it open here. These are the BIOS chips, the Amstrad 40043 and 40044, the even and odd addresses respectively. There's an HD 146818 real-time clock. There's an 8237 DMA controller. And over here we have the graphics RAM. So these are 41264 chips. So they're 64 kilobits by 4 bits each, and so if you have a pair of those, that will be 64 kilobytes. And that's actually 4 times the memory that you'd have in an ordinary CGA card, and that's because of that extra 16 color mode that this machine has. It's also dual ported RAM, so no snow like you get on the original CGA card. Down here we have a couple of crystals. One is a 240-100, which I presume is 24 megahertz. It's not exactly what I was expecting to find. Presumably that's divided by 3 for the CPU, but maybe the graphics chip runs at 24 megahertz, 3 times the speed of the CPU, which would actually match what happens in the PC. So here we have a 286-100, and presumably this is just twice the speed of a normal NTSC chip, which runs at 14.31818 megahertz, that you'd find in a PC. So that was another interesting thing to stumble upon. There's an Amstrad 40078 character ROM, and then there are 3 chips here, the big square ones, which are the chipset for the machine. The 40041 is actually the VDU, the video display unit, in other words the graphics chip. So this is the one that we're going to try and time and figure out what it can do. It also does a little bit of other logic as well, but I won't go into any details here. There's an Amstrad 40039, that's a bus gate array, and a 40040, which is a memory gate array. Obviously there's an empty socket for an 8087-2 math coprocessor, which we don't have in this machine. And there's also an 8253 programmable interval timer, and that's used for system timer and presumably to run the speaker, and maybe also for the pulse that does the DRAM refresh. So it's probably that will be turning off when we do manual RAM refresh, and I'll talk a little bit about that later on. This is an 8259 programmable interrupt controller, and it's just a chip that you need alongside the 8086 to handle interrupts. Now at the top here we have a Zilog floppy disk controller and an 8250 serial I/O chip, and an interesting crystal, a 1843.2, presumably kilohertz, so 1.8 megahertz. I have no idea what this one does. If you know, let me know in the comments below. Probably that's not going to be relevant to us today, although there is a possibility that it controls the programmable interval timer. Not really sure on that. At any rate, that's basically what we have, and that's enough information now for me to get started on trying to write some code to run this thing cycle accurately. The first thing that I want to do here is to run the code that I wrote for the IBM PC on the Amstrad and just see what happens. And to be completely honest, I'm expecting a blank screen here, but let's run it anyway. And interestingly, there's a little bit of a picture here, although this is not correct. I should have pixels in the whole screen, since this code fills all of video RAM. So something has gone wrong here. I'm not sure what it is just yet. And I actually didn't expect it to get this far, because the first thing this code does is get into what's called lockstep, where the CPU and the display controller are in exact lockstep with one another. The way it works is that I set up a very small CRT-C frame, just a few characters in size instead of being a complete frame like this. And I just run it over and over again with the display off, of course. And the idea is that we then step back essentially pixel by pixel until we get to the very beginning of the frame, and then we know we're right at this point here. And then we go back to full screen frames, and then we should be in complete lockstep. Now there's a few reasons why I don't expect that to work here. First of all, I don't know whether this CRT controller that Amstrad have implemented actually supports really small frames or not. And of course, all the timings are going to be completely different on this machine. In addition to that, in order to detect whether we're at the very beginning of the frame or not, we need to know whether we're in the active region or not. So the active region is the bit where pixels are displayed. And there's a bit in the CGA status register which tells you whether you're in the active region. Now, I happen to know that on the Amstrad, this bit is not implemented properly, and there's a reason for that. The main reason you want to know whether you're in the active region is to know whether it's safe to write to video RAM. On the earlier CGA cards, you'd get a lot of snow if you wrote to video RAM while it's displaying pixels from video RAM. And so you'd wait until the end of the line, for example, when you're in horizontal blanking, to do any updates to video RAM. And that would avoid snow. But on this machine, it has dual ported video RAM, and there's no possibility of snow. So there's no need for this feature typically. Unfortunately, we actually need that information to tell where the very beginning of the frame is. Now, as far as I know, it does support vertical retrace, so we're probably going to have to base everything on that, I would say. So what I really want is some code that will determine the exact number of CPU cycles for a full CRTC frame. And I want to know that down to the cycle, in fact. Now, what's got me a bit worried about that is those two crystals we saw. The 24 megahertz one is surely for the CPU. If you divide that by 3, you get the 8 megahertz that the 8086 runs at. And the 28.3 just sounds like twice the NTSC frequency to me, which is what you'd usually use for CGA. So that's different to the PC, where the same crystal is used and it's just divided different ways. So if they're different crystals in this machine, we're not going to be able to get perfect lockstep, so that could be a major issue. Now, I don't know what's going on here. I'm not sure why we've got just a quarter of a frame here. The interesting thing is that I'm doing memory DRAM refresh about 4 times per frame, so if that hangs the first time it runs, then that might explain what's going on here. Interestingly though, I've not got a parity error, so I would kind of expect that if the DRAM refresh wasn't working. So I'm a bit puzzled about that. But if I think about it, actually the code that does the DRAM refresh, the way it works is it puts a little bit of code in each 64K block of memory, and it then executes that code in a sequence. And just executing code in a 64K block is enough to actually refresh the RAM, even with DRAM refresh turned off. So that's how I'm doing the DRAM refresh manually, by running code in those segments. Now, the thing with this machine, I just realized, is this is 512 kilobytes and my PC is 640, and so there's actually a couple of 64K blocks that are not present in this machine, and I'm trying to run code in memory that doesn't exist. So that probably explains what happens here. It does part of the DRAM refresh, and then it hits that block of memory that doesn't exist, and the CPU it just doesn't have valid code to run anymore, and presumably hangs. So maybe that explains what's going on. So I think I'm going to fix that issue first, and maybe this will start working. I should have a little red bar, and yeah, I should be able to move that about, and it's just not there. And if I press Q to go to DOS, yeah, it's just hung. So I think that's probably the explanation for that. So you can see there's an awful lot of problems that we have to work out before we can get this working. Well, good news. It turns out that if you don't try to execute code in memory that doesn't exist, then the code keeps running. So I set it up for 512 kilobytes of memory now, and you can see that it's running because that red bar keeps being displayed. Now, of course, at the moment it's not in sync, and so that red bar is just being displayed at a random location every frame. And I need to know the exact number of CPU cycles for a CRTC frame so that I can get it in exactly the same place every time. So that's something that I'll have to figure out. I still don't know why I'm only getting a quarter of the screen filled with pixels. That's a little bit odd, and this background color I wasn't expecting either, so still a couple of things to figure out there. But I'm not getting any parity errors, and that means that the DRAM refresh is working. So there's two ways that could happen. It could be that I actually haven't turned off the system's DRAM refresh in the first place, and of course if it's just keeping on going, then I'm not going to be able to see any issues. If I have managed to switch it off correctly, that means my code for doing the DRAM refresh automatically by executing code in each 64K block, that's actually working. So let's hope it's the second, but we'll have to look into that. And the other thing, of course, is will it quit to DOS? Is the keyboard handler working? And yes, it is. So it looks like we actually have an almost working program at this point. Still a lot of issues to solve, but this is definitely progress. This is not quite the error message I was expecting, but it is good news. So I turned off the manual DRAM refresh that I was doing and turned off the system DRAM refresh just to make sure that that really does go off. And when I exit the program to DOS, it rebooted and displayed this. I was expecting a parity error rather than this, but I'll take it. So it does really look like the DRAM refresh is going off and my code is working as expected. So that's one issue that we definitely have completely solved. After doing a little bit of investigation in the technical manual, I've managed to answer some of the questions that I had, and a little bit of a look at the schematics finished the rest. So let me show you what I found. So the timer, that's the programmable interval timer, that actually runs on a frequency of 1.193 megahertz, and this is actually a fraction of that 28.6 megahertz crystal, the 2 times NTSC one. So it's actually a fraction of 1/24th of that frequency, and it's not related at all to the CPU frequency. So we know that the CPU and the programmable interval timer are on different crystals, so we're never going to be able to sync those together. Now, this is not necessarily a huge problem because we don't actually need the interval timer to do cycle accurate timing. It's really just a negotiation between the CPU and the graphics subsystem. By the way, that 1843.2 kilohertz crystal that we found, according to the technical reference manual, is for serial I/O, and that's irrelevant to us. We can just totally ignore that. The two crystals that matter are the 24 megahertz one, which is divided by 3 for the CPU, and the one that I've been calling the 2 times NTSC crystal, the 28.6 megahertz one. And we know now that that runs the programmable interval timer. So the question is, which crystal is running the VDU gate array? This one here, the 40041, our graphics chip. So these are the schematics, and you can see that the graphics chip is connected to the dual port RAM, that's our video RAM, as you might expect, and the character ROM. And the relevant thing is this little block in the upper left here. And I apologize, this is not very clear, it's just not a brilliant scan. But unfortunately, the crystal is the 2 times NTSC one. In fact, the frequency here is precisely 2 times, 28.63636 megahertz. And this is bad news because it means that we'll never be able to fully sync the graphics chip and the CPU since they have different crystals. And they'll always be drifting in and out with respect to one another. There's actually another signal here as well that comes from the PIT. It says 1.2 megahertz, but I think they just mean 1.193 and they've just rounded up there. So at any rate, it looks like we're going to have to do something a little bit tricky here to make this work. So the thing that springs to mind is to use the programmable interval timer. We know that that can be 100% synced with the video chip since it runs on the same crystal here. And we can set it up to fire an interrupt at precisely the same place every single frame, really down to the pixel. The problem is that the thing that's going to respond to that interrupt is the CPU, and unfortunately that's just on a different crystal, so it's going to respond on the next available CPU cycle. Now that's not as bad as it sounds. I did some calculations, and in the 320x200 mode I think it works out to about 1 pixel's worth. That's 1 CPU cycle. So probably we're going to be able to set up an interrupt that'll get some code running on the CPU at the same place every frame within 1 pixel. So it's going to jitter about by just that much. So that's not too bad. It's not as good as what we had on the PC, but it's pretty good. Now, it's a little bit complicated to do this. If the CPU is running some other instruction, the interrupt has to wait for that to finish. But you can halt the CPU and just have it sit there waiting for an interrupt. So I'm going to have to set it up so that just before the interrupt fires, the CPU goes into halt and waits for the interrupt to fire, so there's nothing happening when the interrupt comes. And I think that should enable us to get pretty close to pixel perfect, and we'll see how that goes. The first thing that I thought I would do is to just try syncing the CPU directly with the graphics chip without the programmable interval timer. And so what I think my code is doing here is it draws a little red bar just by changing the background color very briefly, waits a little time and then does it again. And I think because this CPU is so fast, I'm actually getting that happening twice per frame instead of once. And you can see it's out of sync at the moment. The number of CPU cycles between each repeat is not exactly the right number of cycles. So it's happening, I think, too early each frame. But what I can do here is press a key which will add one additional CPU cycle per frame. And we'll just keep doing that to try and slow down the movement and try and get it so that it's firing at exactly the same place every frame, and we'll see if that's possible. And I have to admit, it is actually slowing down, so maybe we'll get very close. So yeah, that's slowed down a lot. I'll just keep going here. Wow, that is actually really close. I'm very surprised about that. I just assumed that these crystals would be so far out of sync very, very quickly, as the temperature changed or whatever, that it'd just be a total mess. But actually they seem to be very, very regular. So, well, fingers crossed. I'll just add one more. Look, now it's going back the other way. So now we have too many CPU cycles. So it's not possible to find an exact number of CPU cycles that's exactly right. And that's exactly what we expect. I mean, one crystal does not have a frequency that's an exact integer multiple of the other frequency, and so we were never going to get this to work completely, but I have to say it is a lot better than I thought it would be. So that does give me some hope that when we use the programmable interval timer that we're actually going to get a pretty good result here. Well, the astute amongst you probably realised that when I had the same pattern appearing twice on the screen, I was basically adding an additional processor cycle at the top and at the bottom at the same time. So in other words, 2 cycles per frame instead of 1. So I wouldn't be able to get the slowest possible movement that way. So I spent a lot of time trying to figure out what the right number of cycles is to get the pattern once per frame. And in the end, it turned out to be a surprising value. It was about 20 or 30% different from what I'd expected. And so that still needs some explanation, but at any rate I did get it finally in the end, and now it's moving at about 40 pixels per second. Now watch what happens when I add one more cycle here. Instead of stopping or slowing down, it just remains at the same speed. It didn't make any difference, and believe me, it really is adding an additional cycle here. Now I'll add another one, and it goes back in the other direction at twice the speed, about 80 pixels per second. So that's a difference of about 120 pixels per second, just in round numbers. And I did the computation, and this turns out to be 2 processor cycles worth. So it's surprising that only every second processor cycle that I add makes a difference. You'll see that's the same speed, and now it's 120 pixels per second faster again. So in other words, the processor isn't determining the granularity here. Something else is running slower than the processor and is involved in this whole process. But it's not video RAM, because I'm not actually writing to video RAM for these little red bars. This is just where I'm changing the background color to red very briefly and back again. So it's something to do with that process is causing this 120 pixels per second or 2 processor cycle delay. So I looked in the technical manual and I think I've figured out what it is. Once again, sorry for the poor quality of the images here. These are just scans of the technical reference manual online, and this is a block diagram of the entire machine. So here's the CPU, and it's connected via a 16-bit data bus to the memory gate array and to the system memory. Now all of this runs at the same speed as the CPU, 8 megahertz. But then we go via this bus gate array here, and it steps down from a 16 to an 8-bit data bus. And that is what's connected to our VDU gate array, our graphics chip. So basically when I'm changing that background color, the CPU sends a port access that goes along the 16-bit data bus via the bus gate array and the 8-bit data bus to the graphics chip. So we're looking for something along this pathway which is running at half the speed of the CPU. And it turns out, according to the reference manual a little bit further on, it says that this 8-bit data bus is running at 4 megahertz, not 8. So that's the thing that's at half the speed of the CPU. And so that's our limiting factor right there. So we'd need 2 CPU cycles at 8 megahertz for every 8-bit data bus cycle. And so that's why we have this 120 pixel per second difference instead of what I'd expect, which would be closer to 60 pixels per second. So we've explained exactly why we can't get a difference of just one CPU cycle, but it's always 2 CPU cycles at a time. It's because of this limiting factor, this 8-bit data bus running at 4 megahertz. Well, I also realized that in order to check for glitches in this graphics chip, I don't actually need to stop the movement altogether and get very precise control over where things are happening. I can actually just let it scan through by just drifting naturally the way it already is, and that'll check all of the different locations in the frame. And so basically this is visual mode in my code, and instead of changing the background color very briefly up here and then down here, instead I'm using the time to change one of the registers in the CRT controller chip, the graphics chip that we're trying to study. So in this particular case, I'm changing the vertical displayed register, which is responsible for the number of characters displayed in the vertical direction. So I'm changing it to one value up here and then back to the original value down here. And because of this natural drift, I'm changing that at a different point every frame, and I'm going to go through all the locations in the frame this way. Now I've actually already been all the way around, and it really didn't glitch at all. On the HD6845 and MC6845 that are used in the IBM CGA card, you get all sorts of glitches. Things will flash on and off the screen, or the screen will flash, or it'll jump back and forth, or there'd be extra half characters over the end of the line, and so on. There are all sorts of things that go wrong, but not here. It's dead smooth. So that indicates to me that at least for the vertical displayed register, at least for the values that I'm currently setting it to, this thing is actually working flawlessly. Now I'd be really surprised if they managed to come up with a complete CGA implementation that was totally flawless, and that's what we hope to find out for the first time. But to do that, I'm going to need to check all of the different registers for lots of different values. Well, I just noticed something interesting that I overlooked. This change, due to changing the vertical displayed register, is not taking effect line by line or even character by character. It's really smooth movement, basically pixel by pixel. And that's not what happens with the IBM CGA card. The chips that are used in that basically take effect character by character at best, and even then there's lots of glitching. So maybe we can do something with this that you can't do with CGA. But there's also something weird going on, because I don't have characters displayed from the top of the screen down to this point. For some reason it's blanking the portion up until the first register write. And I don't really know why it's doing that, given the values that I've chosen here. You can actually do this with the IBM CGA card, but not with a write to the CRT controller chip. There's an additional register called the mode control register with a bit that blanks the display, or at least displays the background color. And as far as I recall, that does actually take effect down to the pixel. So maybe it's similar to that, but I don't really understand why they've implemented that here in the CRT controller chip. Now, even if we have control of when that register write happens, it doesn't mean we're going to be able to control every pixel on the screen this way. First of all, there's the 4 megahertz thing, which means basically every second pixel. And of course, the crystals are not in sync, so that could add another pixel or so of slop. And in addition to that, the register writes themselves take time to take effect. When we were changing the background color, for example, I'd change it to red here and immediately back here, but you can see there's quite a bit of delay there, and that just reflects how long it takes to do a port access, and it's also exactly the same amount of time that it takes to do a register write to the CRT controller chip. So we're definitely not going to get control down to the pixel this way. But one effect you could do is to put a static image in VRAM and not change it at all, but basically only display a certain portion of that image. For example, turn the display on here, off here, and so on each line, just to display a rectangle's worth of VRAM at a time. And because we can control very precisely where the first write happens in the display cycle, we can effectively move that rectangle around, showing different portions of the video RAM. And so that would be a really cool effect, but of course using that mode control register you can pretty much already do that with the IBM CGA if I remember correctly. So I don't really know why they've implemented this blanking here, very mysterious indeed. Well, I found some interesting information in the technical reference manual. Here's the registers in the CRT controller chip and what they're supposed to do. And all the ones with dashes are not implemented on the Amstrad, they just don't do anything at all. And the ones with square brackets here, you actually can't change yourself. They're set automatically by the chip when you change graphics mode. Now that might seem limiting. On CGA I can set the vertically displayed number of character rows to anything I want, regardless of graphics mode, whereas here it's fixed for basically full screen display. Now, it says in the manual that if I put 0 in these registers, it will just display the border color and it basically turn the display off. So we've seen that we can do that on an almost pixel by pixel basis. So that's actually more flexible than what you'd have with CGA in a certain sense. There you'd only be able to change the number of character rows that are displayed on the screen. Here I can actually basically display whatever part of the screen I want, whenever I want. So that's actually maybe more flexible, which is kind of neat. Now I should have explained earlier that when you want to change one of these register values, you actually have to do 2 port accesses. The first, which you usually write to port 3D4 on CGA, changes the register number, and the second, which you usually write to port 3D5, selects the value that you want to put in that register. And on the Amstrad though, these port addresses are repeated multiple times for reasons I don't really understand. So it still covers 3D4 and 3D5, but if I want to change the register number, I have the option of writing to 3D0, 2, 4 or 6, and similarly odd values in between for setting the values. So if you've got an idea of how that could be used in a cunning way, let me know in the comments. I thought maybe it was just so that you could change a value with a single write instead of having to do 2, but I can't see how that would work, and in any event, on most PC systems, not all, you can do a 16-bit write to 3D4, the low 8 bits will go to 3D4 and the high 8 bits will go to 3D5, so you can kind of do it all in one operation. It's a little bit slower, but it's still possible. And so I don't really see how that would be different here. The other thing that's occurred to me is if these values are being changed automatically just by changing graphics mode, I have to wonder how fast you can do that and whether you can do it in the middle of the screen. Now of course the manual says that in order to change graphics mode you should first blank the screen, or if you want to change one of these values there's a whole process you should go through and you shouldn't just change them on the fly. Well, I think it'd be rude not to try, don't you? Well, here's something a little bit disappointing. This program is set up to change the start address. So that's the address that it starts reading from in video RAM when it starts displaying stuff on the screen. Now on the PC, this is latched so that you can only change the start address effectively at the beginning of a frame. The difference on the PC is that you can have multiple CRTC frames displaying on the screen at once, and each of those can have a different start address. But on the Amstrad, of course, a frame is always full screen. It's kind of locked in, and so what I had hoped was that I could change the start address anywhere on the screen. So this program is just like the other ones that we've seen already. It makes one change here and then changes the value back down here. So I'd hoped that we'd get something weird happening just in a certain portion of the screen. But let me show you what actually happens. You can see everything just sort of shifted left by one character, and that's because it started reading from video RAM one character later than it otherwise would. If I press it multiple times, you can see it's just shifting across like this. But there's no weird effect here and here. So that means that it's actually latching the start address until the start of the next frame, which is exactly what the PC does. But as I said, the PC allows you to have multiple frames on the screen, and the Amstrad doesn't. So this is actually less flexible. So yeah, a little bit of a disappointment there. Well, this is potentially more interesting. This program changes the number of scan lines per character row. Now, unfortunately, the CRTC can only count up to 128 character rows in the vertical direction. So in graphics mode, if you want a resolution of 200, you have to have 2 scan lines per character row. Well, here I've just changed it to 1 scan line per character row, so everything's bunched up to half the width. It didn't unlock additional video RAM that's in this machine, unfortunately. It just repeats the same information twice, which is slightly disappointing. But at least I can actually change this value and it works. Now on the PC, I can also change it at any point on the screen. So let's try that here. So I changed it to 2 down here, and you can see it widens out, and then back to 1 again for this portion of the screen. So that's working the same as on the PC. And look, we've got a glitch as well, which is interesting. Now that is more interesting because this is really Amstrad specific, and it'll be really interesting to figure out what's going on there. And you can see as it sort of drifted out of whatever range that glitch was occurring, it's disappeared again. Now, of course, I can also set it to other numbers of scan lines per character row, so 3, and it widens out a bit more, 4, 5, and so on. And I've checked, there are 32 different values you can set it to, just like the PC. So yeah, apart from that glitch, which will be interesting to look into, this is the behavior that you expect in ordinary CGA. Well, I already managed to figure out what causes this glitch here, and it happens on the PC as well, actually. So it happens when you're changing from a higher to a lower number of scan lines per character row, and if you've already passed the lower value, its only choice is to keep counting until it wraps around. So for example, if it was changing from 2 scan lines per character row to 1, and it was already on the second scan line for the current character row, it's just going to keep counting up 3, 4, 5 up to 32 before it wraps around and gets back to 1. So unfortunately this one was easier to explain. There is another little glitch that happens on the other side occasionally as well, just very briefly, a little flash, and it's probably just a single character position where there's a little glitch. I think you saw it just happen now. And yeah, I don't think this is very interesting. It's just one very small timing glitch in the chip, and that's it. So yeah, unfortunately nothing new here really that we can exploit. Well, you might think that we've got lots of registers to go and a lot to find out about the CRT controller chip, but it turns out all the remaining registers are for the cursor, and that's not actually available in graphics mode. So we're basically done with that chip, believe it or not. So I thought I'd switch now to changing graphics modes. And as you might remember, the Amstrad has this 16 color mode called Mode 2. It's very similar to EGA. It's a planar mode, and basically it has additional graphics RAM in the machine to handle that. So I thought I'd try changing into that mode in the middle of the screen and then back out of it on the same screen to see what happens. And the manual says that this should be a mess, but lo and behold, it actually works. So this is the 4-color CGA mode and the 16-color mode here. And it really does seem to be taking effect essentially on the pixel, which is really amazing. But as you can see, there's a few issues here. So the first issue is that in order to display 16 colors here, one of the registers needs to be set to all ones, and that register is also used for the background and border color in the 4-color CGA mode, which is why it's all white here. So I could actually add an additional register right to change that register value when I'm changing modes, and that would certainly deal with the issue, but then you get a gap between the two modes about the width of a register right, and so that's not really what you want. It'd be alright if it was over here in the border region, but not if it was in the middle of the graphic. And I haven't thought of a nice way of getting around that. The other issue is that these modes use memory in a very different way. The 4-color CGA mode basically behind the scenes just uses every 4th byte of physical video RAM. And the 16-color mode of course uses all the bytes, but the layout is also very different. Each pixel is just 2 bits in the 4-color mode, whereas in the 16-color mode it's planar, so there are 4 bytes required to make each 8-pixel block, and they basically represent the 4 color planes of the pixels, and so each pixel then is just 1 bit in each of those bytes. So that's really quite different, and so any interface between the modes would have things really quite messed up because of that. So you're more or less stuck really with just having a certain number of lines in one mode, a certain number of lines in another mode, and so on, if you want everything to be really smooth. And that's a little bit boring. You may as well just use a 16-color mode for the whole screen in the first place. There's not anything you're going to be able to display in a 4-color mode that you couldn't display in a 16-color mode, and you have plenty of VRAM, so that's not an issue. But one thing you could do is do things a little faster. It's actually quite fiddly to do bit twiddling to set individual pixels, and essentially what you have to do when you change the color is change a certain register in the chip, and that is really time consuming if you want to do it pixel by pixel. So the 16-color mode can be quite expensive depending on what kind of operation you want to do. For some things it's actually way faster than the 4-color mode. So if you had some graphics on the screen that you wanted to update really rapidly with one type of graphic, and some other graphics that you wanted to update really quickly in a different way with the planar mode, then this would actually be really great for that. So the only other question remaining for me is what about the other modes? Can I also switch into those, like text modes and the 2-color mode and so on? And it turns out that for the most part you can. You can see there's a little bit of glitching going on here. It's not quite as smooth, and it depends on things like whether the dot clock is the same and so on. So I won't go into all the details here, but you can actually fiddle around with the various other modes, and they do, for the most part, switch relatively smoothly with some possible glitching. Actually, there's quite a lot of glitching there. But at any rate, I'm glad this works. It's just a little bit difficult to come up with a really good case for actually wanting to do this in practice. So far it's been a little bit of a bust with this chip. There isn't really that much interesting to find out. So I'm hoping that when we come up with the schedule for the wait states when writing to video RAM, which we haven't done so far, we've just been playing with registers, that we'll find something interesting there. Well guys, I've done it. I got it to fire every frame at exactly the same time using the programmable interval timer rather than counting out CPU cycles. And the programmable interval timer is on the same crystal as the graphics chip, so there's no problem getting it to fire off an interrupt at exactly the same place every frame. In fact, it's exactly 19,912 pit cycles per CRTC frame. Now, of course, I still have to use the CPU for that. It has to respond to the interrupt, and it has to send out the port access to change the background color. And because the CPU is on a different crystal, that means it has to wait for the next available CPU cycle to respond to the interrupt. And because of that, we're getting just a little bit of jitter. It's less than I thought. It's only about 1 pixel. So this is pretty precise. Now, of course, I had to do a lot of things to get it to this point. I mean, first of all, I had to turn DRAM refresh off. You can't use the DMA controller for that. It fires really often, and this just interferes with everything. So that's off. And to prevent parity errors, obviously I have to do DRAM refresh manually using the trick I explained earlier, executing code in every segment of RAM, which charges up those little capacitors and stops you from losing the RAM contents. Now, one problem I ran into is that part of the code that I was running for that was in the interrupt vector table right at the beginning of memory. Now that's fine if you're not using interrupts, but now I am. I had to shift that about so that that would work. But I got it going in the end, and I'm pretty happy with the result here. Now, the other thing I had to do to get rid of jitter is to put the CPU into halt mode just before the interrupt fires. Actually, it fires just in the upper right corner of the screen, by the way. And this, putting it into halt mode, stops the CPU running instructions. And so it doesn't have to wait for the current instruction to finish executing when that interrupt fires. It can respond to it immediately with no delay, and that gives you really precise control. So that's how I've got it the way it is, and I don't think you could do better than that. One thing that's not quite right is if I restart this code, which I can do just by pressing a key here, it will sometimes move by 1 character. It'll move 1 to the left eventually if I do this enough times. It's just going to make a liar out of me for now, but if I do this, there we go, and it shifted 1 character to the left. Now, this is because every time I restart this code, it has to figure out again where the start of frame is. And I can't use the tricks that Rianigni developed for Lockstep on the PC to do this, because he uses the status bit for the active region of the display, and that's not implemented on this machine. Not only that, but he also uses really small frames of just 4 characters or so, and you can't do that on this machine either. It always assumes full screen frames. So instead, what I've done is I've polled the status bit for the vertical retrace, which only happens once a frame. And yeah, that's really slow because you could be here, and if you shift by 1 character every frame, there's a hell of a lot of characters to get you back to the beginning of the frame. So what I do is, first of all, I figure out roughly where the start of the frame is. And actually there's a really long CPU loop that does that. Each iteration takes quite a bit of time. So you never get exactly the start of the frame this way. But then I start the interrupts running, and I make them 1 character short per frame. So it'll always end up doing the interrupt 1 character earlier every frame. And every frame I poll the status bit in exactly the same point in the loop, and eventually it will hit the start of the frame. It takes quite a while. You can see it's like 1 or 2 seconds to do that. And eventually it'll say, now we're at the start of the frame, and that's how I measure it. But for some reason or other, it sometimes misses the start by 1 character. Maybe that's just because my code is not good enough, or it could be just down to this CPU jitter. I really don't know exactly what's causing that, but it's good enough for what we want. So what I want to use this for is to figure out the schedule of wait states for reading and writing to video RAM. Whenever the CPU wants to put a pixel on the screen or read a pixel, it has to wait until the graphics chip is ready, and the graphics chip tells the CPU to wait using something called wait states. So what I want to figure out is where are the no-go zones, maybe where the graphics chip is reading the graphics RAM itself, for example, and it can't allow the CPU to access it at the same time. If I can figure out exactly where those no-go zones are, then it'll be completely safe to do accesses to video RAM in all the other locations, and we should be able to get an optimal schedule for accessing video RAM for pixel information. So I tried to do this years ago. I didn't know all the techniques I know now, and so I was unsuccessful. I did manage to use the fact that these wait states would hold the CPU up, like teeth in a gear almost, to auto sync every frame, and that enabled me to do some raster bars on the screen without using the timer. And this was a nice trick, but I really wanted to figure out this schedule of wait states. So let's give that a go and see if we can do it. Well, this seems to have been more or less successful. I padded things out so that the jitter is now happening just before the start of the active region. And actually I'm now doing a DRAM write. So I'm writing a single byte to video RAM, and I'm doing it just before I do this background color change. And what we'll see is, as we move this thing slowly across to the right, we'll find that there are certain character positions that it can sit in and certain that it can't. And the ones that can't mark out those wait states. So let's see what happens if I add an additional 4 CPU cycles. So move it right. That should move it a little bit more than 4 pixels to the right. Let's see what happens. Basically there was no change there, and if I press a key, so now it's actually shifting by about a character at a time. And it seems to me that basically something about these DRAM writes has to happen on a character boundary, which is really interesting. So because I'm sometimes ending up on one side and sometimes on the other side, it's sort of flickering between 2 different character positions. Let me add another 4 cycles, so I should be just over a character in now. And yeah, nice and stable, it ends up just over a character in. I'll do it again, and I end up in the same place again. Sometimes it's actually flickering back, I think. So let's just restart the code a few times and see if anything changes with that. It doesn't seem to, pretty much seems to be roughly the same place every time. So now I'll do another 4, so I should be 2 characters in now. And not quite, but if I restart the code, it suddenly jumps forward 1, 2, 3, 4 characters forward. And this is exactly what we're looking for. This means that it's jumped over a wait state. So it's now arriving just a little bit too late for that character position, and that's pushing it out to the end of the wait state. That's the first time that it can really appear. So this is exactly what we wanted, and all I have to do is just keep running this code and checking all the positions that it's allowed to appear in and all the positions it's not allowed to appear in, and that'll map out exactly where the wait states are. So that is really cool. So I'm going to run this through off camera. Of course it's going to take me absolutely forever to figure out where the positions are, but hopefully there's a nice regular pattern, and I'll report back in a moment. Well guys, interesting results here, but unfortunately not what I was hoping. I did find a block of 3 locations that seemed to be a no-go zone at the beginning of the line and another 3 at the end, and actually that repeated on the next line in exactly the same places. And maybe that even goes to the bottom of the screen like that. But this just can't be the only places where there's wait states, and in fact I saw indications of them elsewhere where it would jump by a big distance between 2 positions. But as I shifted along further, I found that I could actually get into all of those positions in between. So it's really not a no-go zone at all. So I actually don't know exactly what's going on here, but what I think is happening is that for each pixel within a character, it has a formula for how long it should make the CPU wait. And the only problem is that we have no idea whatsoever which pixel of the character our write request is going to arrive at the graphics chip. And the reason we don't know is because the CPU is not in sync with the graphics chip. So unfortunately, even if we knew what formula the machine was using, and there's no way to figure that out with just character position level precision like we have, even if we knew, we wouldn't be able to use that information anyway, since we never know what the synchronization of the CPU and the graphics chip is. So it looks like we're completely out of luck at this point, and unfortunately this is just the way that retro research goes sometimes. Probably the only way you're going to get any information about this is with a bus sniffer or something like that, so some kind of hardware. But as I say, even if I had the information, I couldn't use it for graphics. So this is really where this story is going to end, unfortunately. And I'm going to cut the video here. I won't actually do a normal outro since the video is already long enough. I will report that the other Amstrad machine that I told you about at the beginning of the video, unfortunately, I have not been able to find a floppy drive that's compatible with it. Really weird. So that, unfortunately, is also going to go on the shelf for a long time probably until I can get one that's compatible. And that seems to be a really difficult thing to do. Yeah, hopefully we'll be back soon with another topic. It won't be the Amstrad after all. And yeah, this is just the way the cookie crumbles sometimes. Retro research can be painful and unfortunately disappointing at times, but at least we learned something about this system that we didn't know before. Anyway, I hope you found this interesting. If not, let me know in the comments below, and we'll see you in the next video. Bye!